Hello and welcome. Today, we're exploring a groundbreaking paper titled Transformers Without Normalization. Authored by Jiachen Zhu, Xinlei Chen, Kaiming Yann LeCun, and Zhuang Liu, this work challenges the long-standing belief that normalization layers are essential in transformer architectures. Let's delve into how this research proposes a novel approach to transformer design and its implications for the future of AI. Transformers have revolutionized modern AI. First introduced in 2017, this architecture has become the foundation for many state-of-the-art models, especially in natural language processing, NLP. The attention mechanism at the core of the transformer enables the modeling of complex dependencies in data, leading to significant advancements in tasks such as machine translation, text generation, and more. Beyond NLP, transformers have also made substantial impacts in fields like computer vision, speech recognition, and bioinformatics, demonstrating their versatility and widespread adoption. Normalization layers are a staple in modern neural networks, helping stabilize the distribution of input data. The purpose of normalization is to reduce what's known as internal covariate shift, which makes networks easier to train. It also improves generalization, meaning the model performs better on unseen data. In transformers, layer normalization, layer norm, is the preferred method, ensuring consistent results in many tasks. Now, let's delve into the breakthrough proposed by Jiachen Zhu and colleagues. Their research suggests that normalization layers may not be necessary for achieving top performance in transformers. The paper introduces a novel architecture called the Normalization-Free Transformer. Accepted at CVPR 2025, this approach challenges the conventional wisdom about normalization layers and proposes a new direction for future AI model optimization. To replace normalization layers, the authors introduced Dynamic Hyperbolic Tangent, DYT. This simple technique allows transformer models to perform just as well, or even better, without normalization layers. Remarkably, implementing DYT requires only 9 lines of code, making it an easy addition to existing transformer architectures. Thank you for joining this overview of the Transformers Without Normalization paper. This research opens new avenues for designing efficient and effective transformer models, potentially reshaping the landscape of AI architectures. The inspiration for DYT comes from observing the input-output behavior of normalization layers, which often resemble S-shaped curves akin to the tangent function. By leveraging this insight, DYT applies a learnable scaling factor to the input before passing it through the tangent function, effectively suppressing extreme values and maintaining stability. This design allows the model to adaptively control the nonlinearity, providing flexibility and robustness in learning complex representations. DYT's effectiveness was evaluated across a broad spectrum of tasks and domains. In computer vision, it was applied to image recognition and generation tasks, showing performance on par with or exceeding that of models using normalization layers. In natural language processing, DYT-enhanced transformers demonstrated competitive results in language modeling and text generation. Additionally, applications in speech recognition and DNA sequence modeling highlighted DYT's versatility and adaptability across different data modalities. In supervised learning tasks, such as ImageNet classification, transformer models incorporating DYT achieve superior performance compared to their normalized counterparts. The VT models, in particular, benefited from the removal of normalization layers, leading to improved accuracy and reduced computational requirements. This finding suggests that DYT not only maintains the performance levels, but also enhances the efficiency of vision transformers. Self-supervised learning methods, like masked autoencoders, MAE, and Dino, were also evaluated with DYT. The results indicated that DYT does not compromise the quality of learned representations, and in some cases, leads to slight improvements. This consistency across different learning paradigms underscores the robustness of DYT and its potential to streamline transformer architectures without sacrificing performance. In image generation tasks, models utilizing DYT achieved competitive FID scores, a standard metric for evaluating generative models when compared to those using normalization layers. Similarly, Large language models, such as LLaMA with parameter sizes ranging from 7B to 70B, exhibited training losses and perplexity metrics comparable to those employing RMS norm, a variant of normalization. These observations reinforce the efficacy of DYT in diverse generative and language modeling scenarios. Beyond vision and language, DIT's adaptability was demonstrated in domains like DNA sequence modeling and speech recognition. In these areas, transformer models with DYT maintained or improved performance metrics, highlighting the universal applicability of this approach. This broad-spectrum effectiveness positions DYT as a promising tool for various AI applications, simplifying architectures while preserving or enhancing functionality. One of the notable advantages of DYT is its minimal sensitivity to hyperparameter settings. The learning rate, a critical factor in training deep networks, had limited impact on models incorporating DYT. This stability suggests that DYT provides a more forgiving optimization landscape, potentially reducing the need for extensive hyperparameter tuning. For large language models, slight adjustments to the initial value of A yielded significant performance gains, offering avenues for further optimization. Implementing DIT resulted in substantial computational benefits. On NVIDIA H100 GPUs, inference speed for models like LLaMA 7B improved by over 52%, and training speed saw a 42% enhancement. These improvements are attributed to the reduced complexity of DIT compared to traditional normalization layers, leading to faster computations and lower energy consumption. Such gains are particularly valuable in deploying large-scale models in resource-constrained environments. The findings from this research prompt a reevaluation of the necessity of normalization layers in transformer architectures. DYT offers a compelling alternative that simplifies model design and enhances efficiency. Future work may explore integrating DYT with other architectural innovations, scaling it to even larger models, and applying it to a wider array of tasks. The open-source availability of the code encourages the community to adopt and further refine this approach, potentially leading to new breakthroughs in AI model development. This work is the result of a collaborative effort among leading researchers in the field: Jiachen Zhu, Xinlei Chen, Kaiming Yann of MIT, Yann LeCun of Meta and NYU, and Zhuang Liu. Their collective expertise and innovative thinking have culminated in a study that challenges existing paradigms and opens new directions for research. The acceptance of this paper into CVPR 2025 further highlights its significance and impact.